Hey everyone, welcome back. Today's explainer is diving into a really specific but absolutely crucial piece of the electricity puzzle. We're going to figure out exactly how we capture and measure the flow of current. So, here's the immediate challenge we face, right? We know that when a circuit is complete, you've got these tiny particles, electrons, just surging through the wires. But you can't see them. It's not like you can just stand there and count them as they zoom past like cars on a highway. So how on earth do we actually measure this invisible action? How do we know if we've got a massive amount of current flowing or just a tiny little trickle? Well, to figure this out, we need a specialized tool and a standard unit of measurement so that scientists, engineers, and anyone building a circuit can understand exactly what's going on inside those wires.
Okay, let's dive into this. The fundamental unit we use to measure electric current is the ampere. But honestly, you're almost always going to hear it referred to simply as amps. And just to keep things super efficient for our notes, amps have a universally recognized symbol, a capital letter A. So whenever you see that capital A next to a number on a circuit diagram or on a piece of equipment, boom, you instantly know we're talking about the exact volume of electrical current flowing through that specific spot.
Now, to actually measure those amps in the real world, we use a device called an ammeter. You might run into an analog ammeter, which uses that classic old-school physical dial with a needle pointer, or you might be using a modern digital ammeter that just gives you a crisp, precise numerical readout on a screen. But here's the thing. Even though they look completely different on the outside, they do the exact same job. They are both built specifically to read the flow of amps.
But having the right tool is really only half the battle. Knowing exactly how to use it is where the actual science comes in. So, the absolute golden rule for measuring current is this. Your ammeter must always be connected in series with the other components in your circuit. But what does in series actually mean in practice? Well, it just means the components are connected end to end, one right after the other, forming a single continuous path. In a series circuit, there are 0 branches. The electrons have no alternate routes to take. They literally have to travel through every single component in the line, and that includes our measuring device.
And setting it up this way brilliantly illustrates what a real-world series connection actually looks like. The ammeter sits right there, directly in the main flow of the circuit. The current flows out of the cell, travels through the open switch, moves straight through the lamp, which is what makes it glow, of course, and then continues right on through the ammeter before heading back to the cell. It's one continuous, unbroken loop. And because that ammeter is sitting dead center in the main pathway, every single electron that flows through the lamp absolutely has to flow through the ammeter too. That is what allows it to take a perfectly accurate head count of the current.
Now, physically hooking up this ammeter does require a little bit of attention to detail. If you look closely at one, you'll see it has 2 connection points, or terminals, where you attach your wires, and they're almost always color-coded. One terminal's red, the other's black. The rule of thumb here is super simple but incredibly important if you want a correct reading. The red terminal of the ammeter has to be connected to the positive terminal of your power supply. It can be a direct connection or through other components, but the path has to lead to positive. Consequently, the black terminal connects back toward the negative side. Matching up this polarity is what ensures the device actually reads the flow correctly.
Okay, hold on. Before we go a single step further, we absolutely have to pause for a major safety warning. This is straight from the source material, and it's literally a safety-first situation. You must never, under any circumstances, connect an ammeter directly across the positive and negative terminals of a cell or battery without anything else in between. See, an ammeter is designed to have almost 0 resistance, so current can flow through it easily for measuring. If you hook it up directly to the battery, you create what's called a short circuit. A massive, completely unregulated amount of current is going to surge through that device, and that can destroy your ammeter, fry your battery, and even cause the whole setup to dangerously overheat. So long story short, always make sure there's another component, like a lamp, in the circuit first.
All right, now that we know how to safely measure current, let's transition into thinking like scientists. We're going to set up a classic electrical mystery. We know current flows out of the battery, through the wires, and lights up our lamps. But what exactly happens to that flow as it actually makes the trip? Does it change? Does it lose energy? Well, by using our newly mastered tool, the ammeter, we can design an experiment to find out exactly how those electrons behave on their journey.
So, let's walk through the experimental setup. We're going to take our ammeter and measure the current at 3 entirely different positions in a basic circuit. First, we'll place the ammeter at position X, which is right before the current reaches the lamps. Next, we'll move the ammeter over to position Y so it's perfectly sandwiched right between the 2 lamps. And finally, we'll place it at position Z,
right after the current has passed through both lamps and is on its final stretch heading back to the battery.
Now, before I just give you the answer, I want you to pause for a second and form a hypothesis. When we close the switch and actually take our readings at X, Y, and Z, what do you think we're going to see? Here are your options. Option A, the current stays exactly the same all the way around the circuit. Option B, the current decreases as it goes around, maybe because those lamps are kind of using up some of the current to make light. Or option C, the current somehow increases as it travels around. Now, I will say, it's super common to guess option B. It just makes intuitive sense to think that because the lamps are doing work, they must be eating up the current, right? Well, let's see what the data actually says.
Okay, imagine we've just flipped the switch on our real-world circuit. The two lamps light up nice and bright. We check the digital display at position X right by the battery and jot that number down. Then, we meticulously unhook the ammeter, move it to position Y right between the lamps, check the reading, and write that down. Finally, we move it to position Z and get our last reading. We line up all three numbers next to our circuit diagrams. The results are in.
And the grand reveal is the reading is identical. It's exactly the same at all three positions. The current stays the same all the way around the circuit. Whether it's position X, position Y, or position Z, it literally does not matter. The number of amps is identical. And honestly, this completely shatters that common myth that current gets used up by the components. Yes, the lamps definitely use energy, but they do not consume the electrons themselves. The electrons just flow right on through, continuing their journey back to the battery at the exact same rate they started.
What's really interesting here is how this connects back to the physical movement of the particles we were talking about earlier. When we measure current in amps, we're basically measuring the speed and volume of that electron flow. If the electrons move more quickly through the wires, the current increases, and our ammeter is going to show a higher number. If those electrons are forced to move slower, the current decreases, and the amp reading drops. But in our series circuit experiment, because there is only one single path for them to take, they all have to move at a uniform rate together. And that is exactly why our reading was perfectly stable across X, Y, and Z.
So, what does this all mean? Well, we've successfully unraveled the mystery. We know what amps are, we know how to wire an ammeter safely in series, and we've proven scientifically that current remains perfectly constant throughout a series circuit. But I want to leave you with a provocative thought directly from our source material's reflection prompts. Now that you know the golden rule, how will you remember this result the next time you build a series circuit? What mental image or trick can you use to remind yourself that the current never ever gets used up? Think about that as you continue diving into the incredible world of physics and electronics. Keep questioning, keep experimenting, and we'll see you in the next explainer.